So, you've encountered a differential equation, but next question is, what kind of a differential equation is it? Because there are different kinds of differential equations, and it's useful to be able to classify and see what kind of differential equation you're dealing with, so you know kind of what kind of solutions it could have and how you might go about finding them. After all, you remember studying equations in algebra and learning that there are different kinds of those. There are linear equations that only involve x to the first power. Those are the easiest to solve. There are quadratic equations where the variable is squared, and those can have two solutions, and sometimes they can have imaginary solutions. You can classify an equation according to whether it just has one variable or two or three. There are logarithmic equations and exponential and trigonometric equations. So with differential equations, there are different kinds of those and ways of classifying those. One distinction we could make is the order of a differential equation, and that's just the order of the highest derivative that occurs in the equation. So, for example, a first-order differential equation would only involve first derivatives. A second-order differential equation would involve a second derivative, and maybe also a first derivative. So, in these examples, the first one and the third one are first-order differential equations. And the middle one, because it involves the second derivative of x with respect to t, that makes it a second-order differential equation. Another key distinction is between ordinary and partial differential equations. An ordinary differential equation is one that just involves ordinary derivatives, because the function that you're trying to find depends on only one variable. With a partial differential equation, that involves functions of more than one variable, and so that involves partial derivatives. Here's an example of a partial differential equation. See these funny looking D's? Those are the symbols for partial derivatives. So this says that the second partial derivative of u with respect to x is equal to a times the second partial derivative of u with respect to t. So here, u would be a function of two other variables, x and t. And when you've got a function that depends on more than one variable, you can't just have the derivative of that function, but you can have the partial derivative with respect to one or the other of those variables. Now, in a beginning course on differential equations, you would spend most or all of your time dealing with ordinary differential equations. But you can take entire classes or read entire books about partial differential equations. And they are important in certain areas of science and engineering. And these are sometimes abbreviated ODEs for ordinary differential equations and PDEs for partial differential equations. So if you hear a math or physics or engineering major friend talk about, oh, I'm studying ODEs or I'm taking a class in PDEs, that's what that means. Now, before we talk about the next thing, let me point out that for any, say, ordinary differential equation where the variables are x and y, and you got y as a function of x, so that means that y is the dependent variable and it depends on x being the independent variable, then an nth order differential equation, first order, second order, fifth order, whatever, could be written in this form here. You know, with any equation, you can line it up so it's got a 0 on one side. If it isn't like that already, you could take what is over here instead of 0 and subtract that on both sides. So this is just saying that you can line it up like that, and in that case, the expression on the left side, the side that isn't 0, is going to involve the independent variable, the dependent variable, the derivative of that dependent variable, that function, and then the second derivative and third derivative and all the way up to the nth derivative, whatever the order is. Or another way that equation could be arranged is it could be solved for that highest order derivative, the nth derivative. So it could have that on one side equal to whatever it's equal to in terms of, well, in terms of the independent variable and then the function itself and all of the lower order derivatives. So for example, if it's a third order differential equation, you could set the third order derivative equal to something involving x and y prime and y prime prime. Now with that in mind, let's talk about the distinction between a linear versus a nonlinear differential equation. So here's how it's defined in a differential equations textbook that I consulted. It says that f of x, y prime, and so on equal to 0 is a linear differential equation of order n if f is a linear function of all of those, the function and all its derivatives, but not necessarily of the independent variable. Otherwise, the equation is nonlinear. And another way to put that is that it's linear if it can be rewritten in this form as some function of x times the nth derivative of y plus some function of x times the n minus first derivative of y plus, and so on down to some function of x times the first derivative of y plus some function of x times y itself equal to some other function of x. Now this looks kind of complicated. This is a concept that's a little hard to explain, but once you get the hang of it, it's pretty straightforward. So think about what linear equations look like back in algebra. If you're talking about an algebraic equation being a linear equation in 2 or 3 or however many variables. So a linear equation involving x and y might be something like 5x minus 7y equals 35. A linear equation involving 3 variables, x, y, and z, might look like x plus 2y plus 4z equals 12. But in each case, it's got an x term and a y term and a z term, and the coefficients on those terms can be any numbers, but you've got a number, a coefficient, times just that variable itself. Not that variable squared, not that variable times some other variable, not the sine or the cosine of that variable. If you have any of those things, it's not a linear equation anymore. So with a differential equation, you have a term involving the nth derivative of y, you have a term involving the first derivative and the second derivative and the third derivative, you have a term involving y itself, and all of those terms can have coefficients that, well, they might just be numbers, but they might be expressions involving x, the independent variable. They just can't involve the dependent variable. They can't involve y or any of its derivatives. So for a linear differential equation, y and y prime and so on can't be, well, there can't be anything going on with them like being squared or cubed or multiplied together or anything like that. So for example, x squared dy dx minus cosine xy equals the square root of x is a linear differential equation. It's got a term involving dy dx, the first derivative. It's got a term involving y, the 0th derivative, and it's got a term that doesn't involve y itself. And then the coefficients on those terms involve x. They can be things like x squared or the negative cosine of x or the square root of x. They just can't involve y or any of its derivatives. Now, here's a nonlinear differential equation, dy dx equal, or minus xy squared equals 15. And it's nonlinear because it's got y squared. You can't have y being squared in a differential equation for it to be linear. And then y times dy dx, oh, right away, that makes it nonlinear because you can't have those two things multiply together. They have to each have their own separate term of the equation. So let's finish up with some examples. In each example, we'll look at a differential equation and try to decide, is it ordinary or partial? What's the order? Like, is it first order or second order or third order or what? And is it linear or nonlinear? So for this differential equation here, ordinary or partial? Well, I see those funny looking D's that indicate partial derivative, so it is a partial differential equation. Here, the function that we'd be trying to find is x, and then x is a function of two other variables, s and t. So it's got more than one independent variable, and then x depends on those two variables. The order, first, we only see first derivatives, and it is a linear differential equation. It's got a term involving the partial derivative of x with respect to s, it's got a term involving the partial derivative of x with respect to t, and it's got a term involving x itself. How about this one? X squared minus 1 times dy dx plus sine x plus 2 times y equals 0. Well, first of all, it's ordinary. I see an ordinary derivative here, but no partial derivative. So here we just have y as a function of x. The order is first. We only see a first derivative here, no higher order derivatives. And it is linear. We've got a term involving dy dx, a term involving y, and then a term that doesn't involve either of those over on the other side. And the coefficients on those terms, they can involve x, but they can involve y, or the derivative of y. How about this? Cosine x dy dx plus 3y plus x plus 5 equals 0. Ordinary or partial? Ordinary. Order? First. Hopefully that's obvious. We just have a first derivative. And linear or nonlinear? Linear. We got a dy dx term, we got a y term, and the rest of it is constant as far as y is concerned. It just involves x. How about this one? Dy dx plus 3y plus x plus 5 equals 0. Still ordinary, still first order, still linear. How about this one? Dy dx minus y squared equals 0. Still ordinary, still first order, but this time it's nonlinear because we have y squared. So if y, the function, the dependent variable, is having anything happen to it, like being squared, it's no longer a linear differential equation. How about this one? X minus 2 times d squared y dx squared plus dy dx plus x cubed plus 1 times y equals 0. It is ordinary. The order is second because it involves a second derivative. It also involves the first derivative, but the highest order derivative is second. And it is linear. You got a second derivative term, a first derivative term, a y itself term, and the coefficients can be as complicated as you want involving x. They just can't involve y or any of its derivatives. How about this one? D squared y dx squared plus dy dx squared plus y equals 0. Ordinary or partial? Ordinary. Order? Second, because it involves a second derivative. And then we've got this first derivative being squared, so it's nonlinear. Now this one here, when you see dx dt, you're thinking, aha, x here is a function of t. So t is the independent variable, and that often happens when you got something that depends on time. So t is the time, and then x is the dependent variable. You got something that's changing over time, something that depends on time. Ordinary or partial? Well, ordinary, those are ordinary derivatives. The order, second. Linear or nonlinear? Well, notice we've got x, the function, times the derivative of x. And you can't have those two things multiplied together in a linear differential equation, so that makes this nonlinear. Now, if we had d squared x dt squared plus 7t dx dt minus x equals t squared. Now, the coefficient on dx dt just depends on the independent variable t, so now it is linear. So this is an ordinary, second order, linear differential equation. Now, there are a few other special types of differential equations, like exact or homogeneous or separable, and that gets into techniques of solving. So You learn about those when you learn about how to solve those particular kinds of differential equations.